Hello and welcome to this tutorial. In this tutorial we are going to discuss the device selection for a particular flyback inverter. So let us discuss this thing. Let us draw first the typical flyback inverter. A typical flyback inverter has a primary switch which we call SP, and as well as it has a secondary side. It is connected with two switches. One this, there is one diode connected here, this we call DAC1, and then there is a MOSFET connected here that we call SAC1, and on the bottom side we have a diode and a switch in the same configuration. This is known as DAC2 and this is known as the SAC2. This point is connected with this point, and this is connected with this point, and across this we have a simple second order circuit, and here we will connect our load, which is our grid. So the question here is, and here sorry, on this primary side, this is connected with a decoupling capacitor. This is CDC, and this CDC is getting its input from this photovoltaic module. So now we have to select this SP, these devices. How we will select it? Now first of all, that the selection of MOSFET is very is very important for proper working of a flyback inverter. Therefore we have to select this SP such that it works well under all conditions. So for the selection of SP should be selected such that it withstands the maximum voltage as well as the continuous current that flows through it. Now the maximum voltage of SP is equal to the VDS of this SP should be equal to V in plus V reflected plus V leakage. Now V in is the maximum photovoltaic voltage that this module can generate. Since I am using a Sanyo HIT N220 module, so the maximum voltage that appears across the output as in my design is equal to, it is somewhere across 48 volts. Then V reflected is what? V reflected is this output voltage, which is this VAC, that reflects across this transformer primary winding, specifically when your secondary side is conducting. So if it is so this value is very simple. This V reflected is equal to VAC peak divided by the turn ratio of this transformer. This ratio is 1:6:6. So whatever our VAC peak is, which now my parameters are, VEC is equal to 120 volt at the rate of 60 hertz. So 120 volt means the 120 volt, if you convert it into a peak value, it will give you around 169 volt. So 169 volt divided by, if you divide it by a factor of 6, and is our 6, so it will be equal to something around 28 volt. And then the last one is this V leakage. This V leakage actually corresponds to the voltage that is due to the leakage spike of the transformer leakage magnetizing inductance. So according to some application notes by microchip technology, this V leakage is nominally from 30 to 35 volt under the full load condition. So now this states that our SP, which is this primary switch, it should have a voltage of SPVDS should be greater than uh, all these three values, which is V in plus V reflected plus V leakage. And now the second thing is this continuous current, because this MOSFET has to bear some, the current that flows through this path. So this continuous current, now we have to calculate this one. So in order to calculate this continuous current, one thing we should mention, we should know about this SP current is that the control scheme of this SP is such that the current will be having a sinusoidal envelope like this. So therefore, when we measure the continuous current capability, we have to keep this in our mind. So now if we are using this Sanyo HIT and 220 module here, then at the minimum voltage, the maximum current will be I is equal to 8.8 ampere. This is through the simulation I have calculated. Now the maximum input current is, it is equal to 8.8 divided by the maximum duty cycle. Now for my design, since it is a discontinuous conduction mode, this delta max is equal to 0.65. Therefore this will be equal to 13.5 ampere. Now let me write this thing here. This continuous current I primary we have calculated, that is equal to 13.5 ampere. But since we have discussed that according to the control scheme of this flyback inverter, the primary current has an envelope of this sinusoidal waveform. Therefore IP should have a factor for the sinusoidal envelope. So therefore IP peak, that is the primary current peak, should be equal to 13.5 multiply 1.41, that is equal to 19.08 ampere. And including the ripple that will be due to that will appear here, the ripple in the current that will appear here, the I primary peak should be greater than, it is somewhere equal to 22 ampere. Therefore, in order to select this switch SP, we have to have a minimum current rating of 22 ampere and the voltage rating of 48 plus 22 and something, it should be around 100 volt. So there is another constraint. The other constraint is that it is better to have the primary switch with low RDS on, because this low RDS on means it will be having it will, if it is not low RDS, it will be difficult to turn on and off at high frequency, specifically when you are switching it at 100 kilohertz. So therefore this SP should be made such that we have a low RDS on and we comply with this I primary peak and this VDS. Now come to the secondary side. So for the secondary side, let me copy this thing here. Okay, let me copy it. Copy. Okay, so we have generated this diagram here. So now is how we can select the DAC, SAC1, DAC2 and SAC2. Remember that when you are switching this SP at 100 kilohertz, when you are switching this primary switch at 100 kilohertz, this dot will also change at 100 kilohertz. Therefore these diodes DAC1 and DAC2, they must be of very high frequency switching. Okay, and that is why we use Schottky diode for this application. So for the diode voltage, again we are having, and this and for this SAC1, This SAC1 will be switched at the line frequency, which is 60 hertz. So this is this, and this will be at 60 hertz. However, this diode must have a high frequency characteristics. Now, how we can find out the diode voltage? The diode voltage is equal to peak grid voltage plus maximum input voltage. And this maximum input voltage means that the voltage that are appeared by multiplying this 6 at this instant. This is V input voltage for this diode. So that will be equal to, if we have a peak grid voltage of 169 volt, provided that this VAC is 110 volt AC. So this will be 169 volt peak plus maximum input voltage will be equal to 330 volt. That is equal to 500, approximately 500 voltage approximately. So if we include the leakage spike, because the leakage will also have an effect on our secondary switches, then including the leakage spike and safety factor, the diode voltage should be greater than 600 volt. And the same actually stands for the SAC1. So that's all for the today lecture. Let's hope if you have any question, you can write in the comment section, and if you like, please do subscribe to my channel. Thank you very much.